So let's continue. Okay, so we had discussed this angular momentum, the magnetic angular momentum, magnetic quantum number, orbital quantum number, energy quantum number. How do we measure these? How do we see these? I mean, you don't just go and look at the electron, but they have some experimentally observable consequences. The principal quantum number, well, we know the spectrum. The spectrum tells us that the energy values are quantized, and in fact, it's a kind of a confirmation of the existence of this principal quantum number. Then to see the magnetic quantum number, and also why it's called the magnetic quantum number, one of the possible ways is to use the Zeeman effect. Now, what happens in the Zeeman effect? You basically take the atom and put it in a magnetic field, or the electron in a magnetic field. Well, you see, if we go back to the Bohr picture, we have an electron orbiting around the nucleus, but it's just like a current carrying loop. Since it's on the average a current carrying loop, it will have a magnetic dipole moment. Do you remember what's the magnitude of the magnetic dipole moment? In general, for a current carrying loop. The electric dipole moment is Q times their separation, if you have two charges. This is the I times mu. I times the current, the area. I being the current, A being the area. And if you have a magnetic dipole moment, and if you put it in a magnetic field, then you get a potential energy due to this magnetic dipole moment given by the negative, the scalar product of the magnetic field and the magnetic dipole moment. So the energy values will shift if you put an electron in a magnetic field. Now let's see how much does it shift. First, let's look at the magnetic dipole moment. This is I times A. Now, what is the current? It's the charge. Well, we have a single electron. Its charge is E. It completes one full rotation in a time 2 pi r over V. This is the current. Well, the area is pi r squared. These r's will cancel, the pi's will cancel. We have E over 2 V times r. Well, let me multiply by m and divide by m. Does m times v times r remind you of anything? It's the angular momentum, the momentum times the radius. So the magnetic dipole moment is E over 2m times L. Now let's see, what is the direction of the magnetic dipole moment of that loop? Do you remember the direction of the magnetic dipole moment? The right-hand rule. Your fingers curl in the direction of the current, then your thumb points the direction of the magnetic dipole moment. So what is the direction of the magnetic dipole moment? It's towards the wall because the charge of the electron is negative. In that case, the current is running clockwise, although the electron is orbiting counterclockwise because its charge is negative. So the magnetic dipole moment in this case is into the screen. What about the direction of the angular momentum? That is towards us. It's again just the right-hand rule. Your thumb in the direction of the radius vector, your palm in the direction of the linear momentum, then your thumb shows the direction of the angular momentum. So you have these two vectors whose magnitudes are related like this, and whose directions are opposite to each other. Well, then I can just say that the magnetic dipole moment vector is equal to minus E over 2m multiplied by the angular momentum vector. Well, this is the classical picture, but it still holds in the quantum mechanics. Of course, with the understanding that all of these are actually operators. The magnetic dipole moment operator is the angular momentum operator multiplied by this number. And that number is what's called the gyromagnetic ratio. So now let's see. The potential energy of this system is then given by E over 2m L dot B. What is the direction of B? You see, B is the externally applied magnetic field. You can just apply it whichever direction you like. So let me just choose the direction of B to be my z-axis. It's a choice. So I can apply B in the whichever direction you like. I haven't specified any z-axis. I can choose the z-axis in whichever direction I like. Well, I would like to simplify my problem, so I will just choose my z-axis to be in the direction of the B field. So the magnetic field is actually its magnitude in the z direction. In that case, the potential energy due to this magnetic field will be E over 2m times B times Lz. But this potential energy is essentially the change in the energy of the electron. Because before there was no such potential energy, now I put the electron in a magnetic field, now the electron acquired an additional potential energy, so the energy levels have changed now. No, I'm looking at the hydrogen atom still. I have the hydrogen atom. There is still the potential between the proton and the electron. So it goes around, the electron still has orbitals, it has these E1 over n squared energy values, it has the L value, it has the M value. Now I took this hydrogen atom and put it in a magnetic field. No, I'm not saying that the initial potential was zero. There was no such potential energy due to the magnetic field. Now I change the potential by adding this new potential term due to the magnetic field, and it shifted my energies. And the shift in the energies of the NLM state is just E over 2m B times M times H bar. This is the shift in the energy of the NL and M state. You see, before, the energies of the NL and M state depended only on the N value, not on anything else. It only depended on N value. But if I put it in a magnetic field, now what happened is the energy acquired a term which is proportional to M. Well, let me write this in this form, mu B times B times M. This is called the Bohr magneton. So you see, before we had, let's say as an example, we had the n is equal to 2, L is equal to 1 state. They all had this energy. ML is equal to 1, ML is equal to 0, and ML is equal to minus 1. They all had exactly the same energy. Now, if I put this system in a magnetic field, the energy values, if ML is equal to 0 didn't change at all. ML is equal to 1. ML is equal to 1, I acquired an energy, mu B times B, and ML is equal to minus 1, sorry, this is ML is equal to 1, this is ML is equal to minus 1. So this difference and this difference are mu B times B. Before, so they were so-called degenerate, they all had the same energy. Now they don't have the same energy anymore, if you put it in a magnetic field. Now let's see what happens in the transitions. You see, we already know the selection rules. Delta L should be 0 plus minus 1. That is one constraint we have. And delta M should be plus minus 1. That is definite. Sorry, my mistake. Delta L has to be plus minus 1, and delta M should be 0 or plus minus 1. So you see, now before, in the absence of the magnetic field, h nu was given by E1 over an initial squared minus E1 over n final squared. Now with the turning off of the magnetic field, well, this is the initial energy before the magnetic field. This is the initial energy, this is the final energy. The difference in the energies was emitted as the photon. Now if we turn on the magnetic field, that is no longer the initial energy. The initial energy is plus mi b mi times b times mu b. This is the initial energy. And the final energy is plus m final b times mu b. So this is equal to, let me call h nu 0 plus delta m b times mu b. So this is the frequency in the absence of the magnetic field. Now when there is a magnetic field, these are the new frequencies. But you see, delta m can only take different values. 0, it can be 0, 1, or minus 1. So now we have three frequencies. H nu, let's say nu b1, which is h nu 0 plus b mu b. H nu b 0, which is h nu 0, and h nu minus 1 in the presence of b, which is h nu 0 minus b mu b. So this is the prediction of this picture. So before, when you see a single line, in the emission or the absorption spectrum, if you put it in a magnetic field, you should actually see 3 lines. Let's say one example can be transition from n is equal to 2, L is equal to 1 states. So here, after, in the presence of the magnetic field, we have 1, 2, 3 lines, 3 states corresponding to the 3 different values of ml. And then it makes a transition to the n is equal to 1. What are the possible values of L for n is equal to 1? Only 0, no other value. So there is a single state. This is ml is equal to 0. This is ml is equal to minus 1, ml is equal to 0, and ml is equal to plus 1. So we have all these transitions. One of them, the second one, and the third one. So corresponding to all those 3 different frequencies. Well, let's see. When do we have this splitting? Well, this splitting is proportional to the magnetic field that you apply. When there is a magnetic field, you will see that this splitting. Well, we had discussed the spectrum. You see, we said that, okay, so here there is an emission spectrum. Here there is a single line. This is what we had discussed. But if you look at that line more closely, what you actually see is 3 very closely spaced lines, not just one of them. How much do they split? Well, that depends on the magnetic field you have. The larger the magnetic field, the larger the split.
Is there any transition between these MLs? ML is equal to 1 or ML is equal to 1?
Well, let's see. Are these transitions possible? They have different energies. No, they have different energies. You see, this has a larger energy than this one in the presence of the magnetic field. That is the whole idea. So since they have different energies, energetically speaking, it is possible. But does it happen? Yes. You say they are all n is equal to 2. In the absence of the magnetic field, their energies will be equal. In the presence of the magnetic field, the energy levels will split. But let's continue. Is this possible? Does it violate any selection rule? You see, what are the selection rules? Let me write it properly. Delta L is equal to plus or minus 1. Delta M is equal to 0 or plus or minus 1. What is the delta M in this transition? 2. So this is not possible. But still, maybe, let's erase that, but why not this one? What is delta M in this transition? Minus 1. So this is satisfied. What about this one? What is the change in delta L? 0. So this is not possible. So this transition violates delta L is equal to plus minus 1 selection rule. Well, it's a nice question. If we didn't have that selection rule, then this model predicts that there should be such a transition. And you can just go ahead and calculate what should be the wavelength and look for that emission or absorption line. And if you don't see it, then your problem is in trouble. Your model is in trouble. What do you mean only in the z-axis? Okay. Why? Well, you see, what is the z-axis? Arbitrary. Choose it whichever way you like. But you see, there's already a preferred axis in your problem if you choose some z-axis in a different direction. Then your potential energy will not have this form. So you have to take into account the x component of P, the y component of P, and the z component of P. If you do a proper treatment of that problem, you will still get the same answer. Okay, so sure. Sure. You see, we didn't assume anything special about the direction of B. B is in some arbitrary direction. Then we just said that, okay, let's choose the z-axis to be in that direction. Exactly. So independent of how you define your directions, if you put your atom in a magnetic field, then the energy levels will split in three. You see, in the final result, the frequencies that you observe, they are independent of direction. They are independent of your choice of your axis. So whichever axis you choose to start with, whichever axis you apply your magnetic field, you will always get this splitting in three. Well, let's see. Yeah, okay. Essentially, when you are measuring this frequency, you are measuring the z component of the angular momentum. So you are making a measurement. Then it exists. You see, what you are measuring here is, when you are measuring this frequency, is actually the component of angular momentum in the direction of the magnetic field. You see, does not exist. The quantum mechanics is weird in this sense that things exist when you measure them. You see, angular momentum, if you measure it, it exists. It will have some value. But it doesn't make sense about the definite direction of angular momentum before you measure it. What do you mean by measurement? This is a measurement. The measurement of the frequency is actually a measurement of the component of the angular momentum in the direction of the magnetic field. I'm measuring the angular momentum, so it exists at that time. I am measuring the z component of angular momentum. I am not measuring the angular momentum. I am only measuring the z component. No. You see, when I'm measuring the z component of angular momentum, only the z component exists. It doesn't make sense to talk about the x and y components. Yeah, that is what we measure. Exactly. We can only determine one component of angular momentum. Just like, I don't know if we had used that terminology, X and P, we cannot determine both of them simultaneously. They are not compatible observables, so to speak. And so X, Y, and Z components of angular momentum, they are not compatible observables. You cannot determine X, Y, and Z component of angular momentum simultaneously. If you determine one of them, you have no idea about the other ones, unless they are all zero. And here, the measurement of this frequency is actually the measurement of the component of angular momentum in the direction of B. They don't exist. You see, the thing is, if you say that it is zero, it means you know its value. If you say that we are not able to measure it, you are indirectly implying that it has the other components of angular momentum, but our technical apparatus, our experimental devices are not able to measure them. That's not the case. Experimentally, we know that that is not the case. Any questions?
Did you say we measure B, magnetic field B, with the same direction, B?
We are measuring the component of L in the direction of B. Yeah. B is something we create. So we just choose its direction. Other questions? So, we said that U is the potential energy. Minus mu dot P. The torque, the magnetic field will be exerting a torque on this magnetic dipole moment, and that will be given by mu cross B and there will also be a force acting on this magnetic dipole moment, which will be given by minus the gradient of U, which is non-zero if B is non-uniform. So if you have a magnetic dipole moment, if you put it in a uniform magnetic field, you see the simplest example is this one. If you just take a rectangular loop, let's say into the screen, you put a magnetic field in this direction. Let me plot it more properly. It goes into the screen. So the current is coming down, going up. So what will be the direction of the force acting on this line? The current is coming towards you. It will be upward. And this will be pointing downward. And if the B is uniform, these two forces will be the same. So, I mean, the total force will be 0. It will just be try to rotate it. So the magnetic dipole vector is pointing in this direction. So it will try to rotate the magnetic dipole vector towards the direction of B. But of course, if B is not uniform, let's say if B has a larger magnitude here and a smaller magnitude over here, then these two forces will not be equal, they will be different. And so it will exert a force, a net force. So let's see, we had already said that, okay, if you take the hydrogen atom, if there is an electron going around it, it will have a magnetic dipole moment. If you put it inside a non-uniform magnetic field, due to this magnetic dipole moment, it will feel a force. So let's say, how do you create a non-uniform magnetic field? Well, this will create a non-uniform magnetic field. Let's say this is the north pole of a magnet, this is the south pole of a magnet. Here there will be a non-uniform magnetic field. And then let's say you send hydrogen atoms through this non-uniform field. Well, you see the force will also depend on the z component of the component of the magnetic dipole moment in the direction of B. You see the force, the potential energy is minus mu z times B. So the force will be mu z times the derivative of B in a sense. Or let's say the z component of the force. The z component of the force will be given by this expression, more or less. So mu z, depending on mu z, which is, let's say, Lz del B by del Z. So Lz can be, in the case of, let's say, L is equal to 1, Lz can be plus 1 h bar, minus 1 h bar, or 0 h bar. So depending on what the value of Lz is, these hydrogen atoms will feel an upward force or a downward force, or they will feel 0 force. So basically, as these atoms move through the system, they will split into 3. This is the ML is equal to 1 case. Well, you are just sending some hydrogen atoms. You have these magnets. You send hydrogen atoms through these magnets. And these hydrogen atoms, they will feel either an upward force or a downward force or 0 force, depending on the value of mz, ml. But for L, L is equal to 1 case. If L is equal to 1, there are 3 different values of ml. 1, 0, and minus 1, so it splits into 3. If L is equal to 5, then there are 11 different values of ml, so it will just split into 11, not just 3. If you have a mixture of hydrogen atoms with some of them having L is equal to 1, some of them having L is equal to 5, well, again, you will have 11 splits. Some of them will be more intense, some less intense.
What is the split of things?
Hydrogen atoms.
One atom?
You just send many atoms. Let's say 5 million atoms. if you create them all such that all the hydrogen atoms are in the L is equal to 1 state, and you send 5 million of them, 1/3 will move up, 1/3 will move down, 1/3 will go straight. If all the hydrogen atoms are in the ground state, then L is equal to 0, so they will just go straight through.
Hiçbir şeyi ölçmeden gönderirsek, yani ölçmediğimizde angular momentum yok, bildiğimiz yok yani.
You see, putting it in a magnetic field and measuring which way they go is a measurement of the value of ML in the direction of B.
Ama ölçmeden öngöremiyoruz o zaman.
You see, again, if you say that we cannot predict it before measuring, you are implying that it exists, but we are not able to predict it. That's not the case. So this is what you expect, and then let's say when you do it, this is what you observe. So what would you then do next? No, not at this level. We just know that they just split into 3 if L is equal to 1. Well, the next thing you can do is, well, you can create, we have electron guns, you can create electrons. Well, just send electrons along a straight line. They don't form closed loops, they don't have any magnetic dipole moment, so nothing should happen. Kind of a boring experiment. Okay, you just send the electrons. Huh? Just not to get bored. I mean, just to see what happens if you have the equipment. Why not? You see, there's an article on the effect of wine, various wine, on the transition temperature of some superconductors. Wine, red wine. Which affects it more? Do they have any effect? There are papers like that. No, they just dip it, leave it, and depending on how much it stays, etc. I mean, it's not. That story is not told, but I'm sure that when they were having some wine, they were bored, so they said, "Why not try?" Let's send the electron. We did it with the. Let's say you have the hydrogen atoms, you have the setup. Send the electrons. And what they observed was the funny part. It's split into 2. This is the observation. Okay, of course, there is a straightaway explanation, as your friend has pointed out. You see, 3 splitting is 2 times 1 plus 1, 3 different values of ml. Here we have 2 different values of ml. Well, ml can, well, if you would like to say ml, but this is nothing like the ml. Ml has either 0 or 3 or 5 or 7 splittings. It never has 2 splitting, but you are right. It acts like ml L is equal to 1/2, but it's not L. That is what we call the spin. So the electrons apparently have this new property that acts very similar to angular momentum. It acts very similar to L, but as L takes the values 0, 1, 2, 3, etc., spin takes the values, can also take the value 1/2. Anyway, we will continue with the spin next week.
Sınavı sınıfı mı?
We will discuss. In most aspects, it behaves identical to angular momentum. If something is true for angular momentum, it's likely also true for the spin.
Diğeri için yani hiç kimse şöyle gitmeyeceğini, şöyle bir hareket yapmayacağını öngörmüyor. Sadece aşağı ve yukarı. Diğerleri eksiz mi? Gidebilir mi belki?
Well, put one more. Not in the z-axis, but in the y-axis, and see what happens.
Ama ölçümü yaptıktan sonra var mı?
No, z-ag, you see, here, let's say, it measures the component of spin in this direction. Put another setup which measures the component of the spin in this direction.
Ama şöyle, onu ölçtükten sonra artık o diğerlerini etkileyebileceğiniz veya
It does influence. It does influence it. You see, here, if you take these electrons and pass these ones and pass them through the exactly the same setup, all of them go down. None of them go up because it has a definite spin now in this direction. But if you, let's say, if you put another setup with a different orientation, take this one, make it pass through another setup with a different orientation. Again, it will be split into two. Pick one of them, not both of them, but one of them, and send them back again through a setup with this orientation, exactly this same orientation. Now it splits into two. You see, we picked the lower going ones, we made another measurement on an axis, on a perpendicular axis, on these ones, and then we send them through the first setup. Then it splits into two. If you remove the middleman, it doesn't split into two. Anyway, we will discuss a bit more in detail next week. If the magnetic field is uniform, it doesn't exert any force. You see, the reason why we choose a non-uniform magnetic field is that the force is proportional to the derivative of the magnetic field. If that derivative is zero, then there is no force, no splitting.